name is Noor, and I'm a PhD student here at School of Computing and Communication, working under the direct supervision of Andres and David Hutchison. My talk today is about challenge detection in cloud computing. Right. So I thought just to start off with the definition of ANISA, because cloud computing means different to different people. But the key point to note about cloud computing is the scalability, shared resources, flexibility, and elasticity. And ANISA defined the cloud computing as on-demand service model for IT provisioning systems. But as I said, that is based on virtualization and distributed computing technologies. So the motivation about this work is I just want to give you an overview of the project called Secret as well. It's sort of a secret, funny name, but we can talk about this in public. So everything is going to be in cloud just because of that certain properties of cloud, as I mentioned, elasticity, flexibility, and shared resources, like the document management system of the e-government, healthcare, and you name it. I mean, soon all sort of critical infrastructure services might move into the cloud without us noticing it. But in terms of the requirement, the requirements vary because critical infrastructure services have much stringent requirements in terms of security and resilience, legal and data protection. And these are the challenges, we try to address these requirements in this project. It's an EU project. I'll explain a bit more detail about this. The problem there is that these services becomes then a potential target for challenges such as cyber attack, denial of service, malware attacks, and you name it. And the existing controls which have been developed in order to protect against those challenges are as much relevant in the cloud environment as well. For example, SQL injection. But if those controls are sufficient enough when the cloud is actually elastic, and for example, when I say elasticity, there's one critical infrastructure service running in one hardware node, and you never know when it's been migrated to some other physical location, for example. So this sort of a control is quite abstract to the users. So these sort of elastic and flexible behavior makes existing controls not robust enough, so they probably have a high false positive rates. So cloud computing by definition is quite opaque. So if there are any problem or failures, so it's very difficult to analyze what caused that failure. So in terms of root cause analysis and attack attribution, there are a lot of challenges which we try to address in this project. The overall objective in the Secret project are quite varying to address the overall problem space of the cloud, starting from service level agreement compliance, risk assessment methodologies. We have colleagues in management school who are working in this objective. And we at Lancaster are working on this third objective about understanding cloud behavior and trying to come up with anomaly detection techniques that are robust with cloud elasticity and flexibilities. And then there again cloud security guidelines, and then we have some partners in Spain, Valencia, their government, and we'll try to exploit all the tools and we develop and the result in their infrastructures. And there's some partners from Finland as well who provide the video surveillance systems. So as I said, the requirements for us is to actually analyze the viability of the existing anomaly detection techniques and try to come up with some anomaly detection techniques which can accommodate the dynamic behavior of the cloud. So two important perspectives need to be used, or I must say consider, in order to develop these anomaly detection techniques. So network level and the system level. Mike Watson, you probably have seen in his talk in the morning, is working on the system level, while I'm working on the network level perspective to develop these anomaly detection techniques. So the key challenges in order to develop those anomaly detection techniques are quite similar to the regular anomaly detection techniques, or I would say regular security. But the problem is about the main key challenge is about if you come up with anomaly detection techniques that is robust with elastic cloud environments, then how should that be operationally applied? And because the normal behavior is keep evolving in the cloud, and the normal behavior and the anomalous behavior is often not precise enough. Okay. So as Mike probably have explained, this test bed we have here, but the key thing to note here is that what we are trying to develop some software components in hypervisor layer to extract some network level features and some service level semantics, and try to correlate that information for better anomaly detection, and that then can be further feed into the resilience component, like a policy-based resilience simulator, which Andres has just explained, and to push the preventive and remediations control, which, for example, a preventive control could be like shutting down one VM0, or stopping the traffic that is directed towards some vulnerable VM. So as I said, statistical approach is one of the very key approach we are taking at the network level because of its strength to detect unknown attacks. And we extract the features from the host, such as system calls, and from the network level we look at the byte patterns and volume and entropy information to apply those statistical techniques. So in previous test bed we had some challenges that we introduced, like Calios. Of course, in a controlled environment, these are malwares we try to introduce into this test bed and try to extract features, and then try to coordinate the network level engines and security level engines, and then feed into these outputs into the resilience simulator. So many techniques can be actually applied into this anomaly detection at network level, but our key focus so far is covariance matrix analysis and principal component analysis to understand, and you can pretty much see the Calios injection on the 10th or 12th feature. We have a 13 feature set that we extracted from the hypervisor layer. System level analysis, this is what Mike has explained. So that's about it. Thank you very much.